Hello everyone, I am Ajay Rotela. Welcome you all. to the first talk of this GeoVigyan WorkDRILL event. We hope you all are fine and well. So today's presenter is Mr. Sabyasachi Kabiraj. He is a senior research fellow at Central Institute of Brackish-Water Aquaculture and a research scholar at Anna University, Chennai. He has published multiple international research articles in Elsewhere, Springer, and other. He as a project assistant at Indira Gandhi Center for Atomic Research. Now we will call our presenter. I request you to please start your session, sir.
Thank you, Ajay.
Yes, sir.
So, a very good afternoon to all. So, I'm sharing my screen with you all. Just a second.
Yes, sir.
Is my screen is visible to all of you?
Yes, sir.
So okay, let's start today's session. So, as Ajay already introduced about me, so myself, I am Sabyasachi Kabiraj, and as he already informed that I am doing as a research scholar, I am doing research in Anna University, and also I'm working as a senior research fellow in ICAR, Central Institute of Brackish-Water Aquaculture. So today I'm going to present about this remote sensing application in land monitoring. So this session will be about little bit basics about remote sensing and its application on land monitoring. So I'm starting my today's session. So the outline of today's session is about what is remote sensing and what are the different types of sensors and imagers, sound, and radiometers. Then we'll talk about satellite orbits. Then we'll talk about the different types of resolution. Then we'll come to the various applications of remote sensing and GIS. Then we'll show some of the case studies which are based on land applications using remote sensing GIS. And these are the things for today's session. So what is remote sensing basically? So the remote sensing is like acquiring information without coming into the physical contact with the object. Okay, so this can be anything, like our eyes can sense any object by reflecting the energy from that particular object. So it's like sensing the reflected energy through the sensor. So it's a type of remote sensing. So you can see that various platform. So first of all, orbital platform, that is satellite, and suborbital platform, that is aeroplane, aircraft. And these aircrafts are directly sending their energy. It can be passive, it can be active. There will be like two types of remote sensing. So that we will talk about in our later part. So these are some of the example you can see here. And here you can see some satellites and aircraft and some local sensors also. So the thing is, what information you want? Yes.
Sir,
Yes.
at the bottom there is a notification. Can you hide that?
Just a second.
At what? Yeah, Google Meet notification.
Okay.
Stop sharing that one.
Okay.
Okay, sir.
Okay, Ajay.
Thank you, sir.
So these are the different types of platform, and this platform will be used based upon your like what is your objective, what information you want to take from the ground. So it's all about your needs, basic needs. So what information do you want and how much detail you want, and the type of detail and how frequent you want to observe that particular object. Okay, so this, based on these particular things, you have to design your sensor, or you have to design your platform, which platform you want to perform. So these are the things you have to consider before designing a particular study. So now we will talk about remote sensing process, how it is capturing the image and what are the different steps it is going through. So the first step is the energy source or illuminations. So here there are two types of energy source. One is directly you can get energy from sun, and the another thing is the sensor itself sending one energy in case of active remote sensing. Okay, so first of all we'll send the energy source, and that energy will go to the atmosphere, and it will generate radiations, and it will finally interact with the target, and thus it will record the energy by sensor, and finally transmission, reception and processing, and we will take that information into our software and we will do the interpretation analysis. So these are the some of the things about remote sensing and how it works. So now coming to the satellite sensors and their classification. So based on orbits, there are two types of satellite, like one is polar satellite and one is geostationary satellite. And based on energy source, as already informed, passive and active. So passive is basically based on like already there are energy source like sun we have, so we don't have to send energy to the object, so it is a passive. And active in the sense, in night we don't have energy source, or whenever we will have cloud, that time also we may not, it may not be visible. So in that case we are using active remote sensing, and in this active remote sensing we are sending a leader. So these types of some of the things we have to send through our sensor to the object. Okay, and then solar spectrum. So these are the spectral radiations. You can see the different spectral bands, and these are something like visible, then ultraviolet, infrared and microwave. These are the spectral bands. So you have to decide your area of spectrum. So for example, my study, whether my study will be based on visible range or ultraviolet range or infrared or microwave. So we have to finalize which particular spectrum we are going to study. So it is particularly based on your objective. Suppose some of the research scholar may be interested in land use land cover, so they can go through this visible spectrum. So in this visible, we'll have three bands like RGB, red, green, blue, and near infrared as well. And then ultraviolet, infrared, these are for like mineral explorations, then finding salt affected land, some different mineral explorations. And also we can use microwave, where the cloudy weather, like invisible, we cannot see the land, particularly land surface, when there will be a like cloudy weather. So in case of microwave, it is possible to see the land informations whenever, like in case of like if there is a cloud, we can see the land in case of microwave. So microwave is a very advantage in the case of cloudy weather, right? And then this thing is measurement technique. So there are different types of measurement like scanning, non-scanning, image, sounders. So these are the things is already available. And then resolutions is very important, and there is a high, low, medium resolutions. And the applications is weather, ocean color, land mapping, atmospheric physics, then chemistry, air quality. These are some of the applications of remote sensing. Now we are coming to the remote sensing systems. So already, as already I informed that there will be two systems, and then one is active and another one is passive. So in case of active remote sensing, you can see here that artificial energy we are sending to the particular objective. But in case of passive remote sensing, there is already existing a natural energy which is sunlight, and we are utilizing that particular sunlight. And this artificial energy in case of active remote sensing system, and these are the example like radar system, solar and sonar. These are the star images there for Sentinel-1. And here you can see whole Landsat series, Spot, then Sentinel-2. These are some of the passive remote sensing, example of passive remote sensing satellites. So now we are coming to the passive sensors. So what are the passive sensors? So you can see, for example, Aster, Landsat, then MODIS. These are some of the passive sensors. And in case of active sensors, there is a LIDAR, then radar, sonar. These are some of the passive sensors. So the important note is passive instrument measure reflected emitted radiation at the top of the atmosphere. All other information it derives from this have some ancillary data. Then imagers and sounders, as already you can see that it can go to the troposphere, how it is collecting the information, and it is going, energy is going through this all other our atmospheric layers, mesosphere, thermosphere. So this information also we can get it. And there is two types of orbital satellite system is there. One is geostationary and one is polar. So you can see here geostationary satellites only captures images through the earth rotational periods, and it is like if you are having interest on these land monitoring systems, you can go through geostationary satellites. And this is polar orbiting fixed circular orbits, and it is above 600 to 1000 kilometer in sun synchronous orbit with orbital pass. And these are the things. And here, if you see the resolution types, here 4 different resolutions are there. And the spatial resolution is something about the pixel measurement and what is the size of the pixel. So that's called spatial resolution. For example, if you have 10-meter resolution and if you have 30-meter resolution, so obviously that 10-meter resolution will be more clear and it will give more information about the particular object. And this is about pixel size. And the second one is temporal resolution. So this temporal resolution is frequency of measurement. Suppose, for example, in one particular place, today, if one satellite is monitored or collected data, then again, when it is coming back and taking the image of the same objective, so that is called temporal resolution, that revisit time of the satellite. So that is called temporal resolution. And then spectral resolution. Spectral resolution, as already I informed, there are different types of spectrum, like visible infrared, visible portion, then ultraviolet, microwave. So it depends on the satellite, what are the information they are providing for. And then radiometric resolution. And this radiometric resolution is one of the important factor of this satellite remote sensing. So it is mainly indicating the DN value, that is called digital number, and it is a gray value which shows the brightness of a particular pixel. And later on we will discuss this. And coming into the pixel, so it is like smallest units of an image, and it is normally it is in a square shape, and it is like representing a certain area of the earth. And here you can see the spatial resolution's importance. So if you see 0.5 meter into 0.5 meter pixel, it is this much clear. And the same image when we are taking is 1 meter by 1 meter, and it is, you can see there is a blurry things, is the information is little bit less. And you can see 2.5 by 2.5, and the information is more or less. And finally, likewise, you can go through and you can see finally 80 into 80 meter, the full object is not visible at all. Now coming to the spectral resolutions, so here you can see, and this side you can see the longer spectral resolution. So this is electromagnetic spectrum. Longer spectrum is this side, and the smallest spectrum is this side. And it is starting from gamma, then X-ray, then these are the ultraviolet, infrared, microwave, radio waves. So this is the different spectral resolutions. For example, if your area of interest in visible, so you can go to the visible zone. It is here located somewhere. And if your area of interest in microwave region, so you can go this particular area. So it depends on your interest. Then if we coming to the this spectral resolutions, so our visible range is 0.4 to 0.5 micrometer, and you can see blue, green, red, which covers blue, green, red. And you can see here multispectral sensors like MODIS will cover this spectral, sorry. And there are hyperspectral images available as well. You can see this informations are giving in very narrow band. So you can see very narrow information it is providing through different spectral signature. You can see here it's very narrow. So hyperspectral is mainly thousand of band, hundred of bands it is compiled of. So if you go to the radiometric resolutions, so here you can see the DN value, and also it is like how much bit it is, that image. For example, 8 bit, 6 bit. So here you can see 12 bit sensor, which is MODIS. So it is providing 4096 gray level information. So it is like denoting the gray level, what is the like different level of brightness. So 1 to 4096. So if it is 10 bit sensor, then the information is less, and likewise it is reducing one by one. So if you see here is an image of 2 level and 8 level, and here is a 4 and 16 level. The image clarity or image visibility is much more narrower, and you can see the clarity is much more clear, right? So depends on the radiometric resolutions, your picture quality also change. Now here coming into the temporal resolution, so it is like revisit period of a particular satellite. And if you consider MODIS satellite, it is like 1 or 2 days or 16 days repeated cycle. And OMI 1 or 2 days, MIS as 0.0 to 8 days. And if you consider geostationary satellites, it is 15 to 1 hour. But it is limited to some specific area of the globe. So now here I have given the all satellite details and their spatial resolutions and temporal resolutions. So it's here you can see that if you see the Sentinel-3, MODIS, and Meteosat, and their scale is also very large. You can see 1,000 kilometer or something around 100 kilometer square. But if you want to study in micro scale, micro level, so you have to go through this satellite, GeoEye and World View and Spot, Rapid Eye. These are very high resolution satellite imageries, and their revisit period is quite less because they are providing high resolution imagery, so it takes time to cover the entire globe. But whereas in this case, that revisit period is much more high. You can see the temporal resolution is increasing from this direction to this direction. So these are the some of the satellites which gives very frequent observations. But whereas in this case, these satellites are not that much giving frequent information, only monthly once or twice, or maybe fourth time in a month. So if you see here, there is a MODIS image of 50-meter true color composite image, which covers this area, this much area. But in the same image, you can see Aster image, 15-meter resolution, and it is giving much more clear information. Same way, you can see the 2,300 kilometer, the width of that, and the same things it is covering 60 kilometers. So therefore, satellite designs are applications oriented. So it is very difficult to obtain extremely high spectral, spatial, temporal, and radiometric resolution at the same time. Yeah. And there are several other sensors can obtain global coverage every 1 and 2 days because of their wide swath. And the higher resolution polar orbiting satellite may take 6 to 8 to 16 days for global coverage. Geostationary satellite obtain much more frequent observation, but at lower resolution due to much greater or vital distance. So coming to the satellite remote sensing applications. So here we can see there is a applications of agriculture and soil resources, land use land cover, then geoscience, then forestry and environment. So if you see the agriculture, remote sensing is a very vital tool. So through remote sensing, we can classify the crop, then we can detect the cropping pattern, how it is changing seasonally, annually, and then also we can estimate the yield of a particular crop. And also we can demarcate the crop area, like how much area of a particular district is occupied by a particular type of crop. So we can also detect the changes of different crops. For example, if 1 year, if you take 5 years interval and how the cropping pattern is changing, so that also we can analyze through remote sensing data. So that is from the view of agriculture. Then if you see soil resources, so we can map soil, different soil type like loamy soil, sandy soil. So these are the different soil types we can map through remote sensing by taking the samples. Then we can also find the land capability, so how much the land is capable of. So first you have to find out the soil types, and based on soil type we can calculate the land capability and irrigability. Then we also can calculate the soil moisture, and there are different sensors designed for particularly for soil moisture mapping. Then also we can identify waterlogged areas, then salt affected soils, eroded lands, and shifting cultivations. So these are some of the soil resource related applications of remote sensing. So in case of salt affected soils, here you can see the different types of, like there will be salt will be there, like non-saline, then highly moderate saline, sodic soil, non-saline, saline soil, sodic soil. There are different types of salt present in the soil. So remote sensing can detect the different type and degree of soil salinity, right? So coming to the land use land cover, here we can detect the land use land cover changes, how it is changing from pre-industrial to post-industrial, now current. So this depends on the satellite images and their time period. Okay. Then we also can map wasteland. So what are the wasteland available in a particular area? And after mapping the wasteland, we can plan, or we can manage the land, how it can be useful for the local people. Then we also can calculate the urban sprawl mapping. For example, how a particular urban is like increasing day by day and year by year, and which direction it is increasing the area, which direction it is increasing. So those things also, like urban trend, those things also we can analyze through remote sensing GIS. Then if we see geoscience perspective, like we can map the different geological type, like rocks. What are the different rocks available? For example, mineral explorations we are using remote sensing. So using remote sensing, like we have different aster images, different bands of aster images. Like if we use short wave infrared, that is mainly useful for mineral explorations, and through that we can identify the different minerals present in a particular area. So in that case, remote sensing will be very useful. So nowadays, remote sensing is widely used for these geological explorations. So identifying the iron ore zone, for example, in Keonjhar districts in Odisha. So they have mapped the iron deposit, major iron deposits area, and after that they have mined those areas. So like that, we can find out through remote sensing GIS different resources in the earth surface. So this is the things. And also coming to the geomorphological mapping, and this geomorphological mapping particularly based on elevations, then we can say based on faults, fracture, and the historical images, all combining we can map geomorphological things, units. And then coming to the groundwater potential zone mapping, and people are thinking how is it possible to map groundwater potential zone as it is underground. So for that, I want to say that it is possible to map the groundwater potential zones. Like we are taking the different parameters which influencing the groundwater. So for example, if we take the slope, so lower elevated areas will have high groundwater potential zone as the water coming from high elevated to low elevated, and that is the trend of water flow. And also we can consider the soil moisture, we can consider soil texture, and after that we can also consider the drainage density. And considering these factors, we can finally make a weighted overlay analysis is there, artificial neural network is there, and using these methods we can calculate the groundwater potential zone mapping for a particular area. So it is possible to find out the groundwater potential zone. So another thing is mineral targeting. So this is already I have explained, and different minerals deposited in various areas and how we can detect. And we have to see the different band combination, and here the bands are very much important, what band you are using, and that you have to see properly for what mineral you are going to explore. So depends on mineral, your band combination will also change because each mineral will have different spectral signatures. So those things is very important before designing the your methodology. Okay, so these things you have to consider. Then coming to the forestry and environment, so you can see forest cover mapping. So we can map forest cover how it is changing, and from prehistorical and historical images, if you take 1980, 1970 or 60 images, and how the forest cover has changed in recent decades, and what trend it is changed, like which direction it is changing, and what are the possible reason for forest cover changing. Okay, and finally we can plan for that particular areas where forest forest cover is vulnerable, and those vulnerable zone we can identify through remote sensing, and finally we can give a management plan for that. And then forest management plan, you can see biodiversity conservations also we can do, like different types of flora and fauna we can map. And environment impact assessment, these things is very important. Environment impact assessment, it can be for anything, for mining region and then for coastal region. So this environment impact assessment is something like it considering all parameters. It will consider soil, it will consider atmosphere, air, then water. So this is very important thing. Then the final thing is grassland mapping. So these are some of the applications of remote sensing in brief. So all area of remote sensing applications we can't cover in a single lecture. It is like huge variety of applications of remote sensing, and it is a very vast area and it is growing very fast. So it is not possible to cover. So here in this slide I have given some of the important things. And now we are going to discuss about the various applications of remote sensing in land. Okay. So here one study they have did in Vietnam Mekong Delta, and here you can see the different land use land cover, and it is every 1 year they have mapped the land use land cover, and you can see shrimp farm, shrimp rice farming, single rice, triple rice, and inland aquaculture. And this side they have mapped the water or flooded area. So how much area was flooded previously and how much it is now, that they have calculated. And you can see in 2000 there was a huge area of water body, you can say water flood or lake ponds. You can see here this blue color indicates the water, and slowly this water become, you can see the volume of water is reducing. And this is happened because of massive construction of dikes or triple rise cropping in the upper zone appears to cause a significant impact on annual flooding region. Okay, so actually this has happened because of dikes construction. So they have constructed dikes in these areas, and the dikes holding that water, and slowly that area become very less water region. Okay, so this is one study. The second study shows, and this is like Coimbatore and Tamil Nadu. So here it has shown how it is grown from one year to another year. So you can see the red color shows the urban area, and this red color shows the in different year urban area. So how it has changed, and finally they have created buffer from the center of the urban area, and that buffer shows, that buffer analysis shown in this graph. And the first one is distance from the city center and the percentage of area of the urban. So here you can see, as the distance from the city center increasing, the area of urban area also decreasing. So there is a trend. The same way you can see the distance from the city center and the vegetations. So the distance is increasing and that vegetation is also reducing. So there is a linkage. And the same way you can see water bodies and this agricultural land and barren land. So there is a detections and analysis using remote sensing and GIS technique. So here is a study by Kabiraj et al. 2022, and in this study we have tried to find out the land degraded areas, and this region is belongs to West Bengal, and this is like Durgapur, West Bardhaman districts, that is Paschim Bardhaman district. And in these districts they have bricks industry, mining industries, and other industries, and these are the mining zones. You can see here these are the mining zones, and how this mining activity has increased day by day. You can see 1990 these are the different black patches shows the mining area, and in 2010 this mining areas has increased. And if you see 2000 how it is and how it was in 2010 and 2020, so like this it has increased, the mining area has increased. And depending on this, NDVI has been calculated, and there is a change of annual NDVI, and you can see these are the region where NDVI is reduced, and this NDVI is an indication of vegetation changes over the area. So you can see there is a minus value of NDVI in this region. So here only we have considered the minus value of NDVI. So these are the vulnerable region where vegetation has increased, vegetation has decreased, the health also decreased. So you can see these are the vulnerable zone of vegetation. Then if you look into the land surface temperature, and this is also like annual change in land surface temperature, and if you see the mining regions here, and it is showing in red color, and we have already we only shown the positive changes of land surface temperature, and these are the highest positive changes. It's about 0.46 degrees centigrade per year. Then we have also considered the evapotranspirations, and it is kg meter square per year. And if you see, these are the zone where that evapotranspirations also reduce because the vegetation is reducing. So there is an absence of vegetations, and if there is an absence of vegetations, there is an absence of reductions of evapotranspirations. So that only there is a link between vegetations and evapotranspiration. And finally, we have shown here, you can see there is a graph which shows the area of mining industries and the mean NDVI. So you can see the area of mining industry is increasing, whereas its mean NDVI value is decreasing. So there is a link between NDVI and mining area. So there is a degradation. And in the second graph, if you see the mean LST in summer daytime and the mining area, so mining area is increasing, and then there is a positive trend of increasing LST during summertime. Also, evapotranspiration, you can see there is a negative relations with mining industries. So based on these parameters, we have created a scenario-based analysis, that is scenario A, B, and C and D, and what are the possible vulnerable region in future. Those things we have carried out in this research article. Now coming to the salt affected land using remote sensing, GIS, and machine learning method. So this is a like kind of detecting salt affected regions through, you have to collect the soil sample and you have to analyze that electrical conductivity of that particular soil sample, and through that we will get the soil salinity value, and that will be the inputs and also validations. Okay, so if you see the methodology in this research article, we have taken Sentinel-2 and Landsat-8, right? The different resolutions. So Sentinel-2 is 10 meter and Landsat-8 is 30 meter resolution. Okay, and we have considered, these are the indices, spectral indices we have considered, and we have considered this only 10 meter bands, and here also we only considered the 30 meter bands, right? And after analyzing this, after calculating these things, these indices, we have given that our inputs is a vector file of soil sample. So we have created a soil sample, and through that we have like calculated electrical conductivity of soil sample, and we have classified the soil salinity, classified in terms of like very low, low, medium, high, based on electrical conductivity value. And after that we have created a shapefile of that all points of soil sample, and we uploaded in Google Earth Engine platform. Now we have trained the model, and we have used hyperparameter tuning, and this hyperparameter tuning is very important in case of random forest model, and we have used this hyperparameter tuning for number of trees and bag fractions. So we have we got that some of the optimum number through which we can get highest number of accuracy, and those particular number of trees and bag fraction we have used in our model. So this hyperparameter will give a value of number of trees and bag fraction, which will give highest number of accuracy, and that number of trees and bag fraction we have used in input as an input in random forest model. And also we have taken the soil sample as an input, and 70% of the training sample we have used for training and 30% for validations. And thus same way we did for these two Sentinel-2 and Landsat, and we have compared those results, both result. And these are the indicators you can see here. These are the indicators, and how these variables of importance is like how much important these variables are, those things shown in this paragraph. And this is the output of salt affected land using Landsat 8, and this is the output of salt affected land using Sentinel-2. And finally, we got a good response using Sentinel-2 data, and it is showing much clear informations as the spatial resolution is higher than Landsat 8. And you can see the salt pan areas, it is showing very high soil salinity, whereas here you can see some of the yellow pixels, and here also you can see some of the salt pan area where it is detected as highly saline, right? So there is a difference in spatial resolution, and thus it creates the difference in output, final output. Coming to the shoreline change analysis mapping. So this study by Misra et al. 2021, and you can see they have considered the Odisha coast and zone 1, zone 2, zone 3, zone 4, and zone 5. They have taken and they have digitized the shoreline in different years. So the year are like 1990, 95, then 2000. Every 5-year interval, they have collected the satellite data and they have demarcated the shoreline. And after demarcating, they have created the transects. You can see this red color transects over here, then here. And after creating the transect, they have analyzed the EPR, that is endpoint rate, how the shoreline changing, and the shoreline change rate is meter per year, and it is highest over here, and you can see these are in minus. So it is erosion and accretion it shows. So accretion is positive change, that is plus, and erosion is minus, that is in red color shows. So there is a accretion and erosion in this, and those values are shown over here. And this also the same, you can see it is like greater than 5 meter per year, and this is shows accretion, which is in green color. So here it is accretion, and the red color shows erosions. So through EPR and the LRR and WLR, and these are like endpoint rate and linear regression rate and weighted linear regression rate. So these are the three methods through which we can quantify the shoreline change, how it is eroding or how it is accreting. So these things we can analyze through remote sensing data. And finally, we can give the proper management plan for that particular coast. So this is again, they have showed that erosion risk, and this is like above 5. The above 5, they have shown that very high and high, stable, then low. So above 5, above minus 5 meter per year, they have taken as a highly vulnerable zones, and these are the red colors is shown very high risk, and these are the yellow zone where it is stable and it's accretion. And finally, they have incorporated the population data, and you can see here there is a well match of these two data, and thus they have incorporated these two data. So here also the same thing, and here number of household. And here in this image, if you see how in 2011 the data shows here, it was that shoreline, and the same shoreline how it was in 2019 and 2016, how it is changing. So shoreline change along the transect near Kodampetta in 1990 to 2019, and it is shoreline change along the transect near Kodampetta 2011. So you can see how the shoreline has changed. So this shoreline is probably 1995, and this is the recent one in blue color, and how the shoreline has shifted from this position to the this position, and this can be analyzed through remote sensing data. Same way here also you can see how it has shifted. And the summary is, remote sensing GIS technique is well capable in detecting land use change, and with the use of different satellite and its resolutions it is possible to assess the changes and quantify the changes. And through assessing the changes, it is possible to predict the future trend, which can help in further planning and management practices in future. So degraded lands can also be identified through remote sensing GIS techniques, and these lands can be reclaimed through proper management. And using shoreline change analysis, coastal vulnerable zone can be identified, and through proper management and planning and management, those regions can be protected. Remote sensing GIS technology, using remote sensing GIS technology, unused land can be identified, and those unused land can be used for livelihood purposes for the local people. So thank you. That's all for today's lecture. So if you have any questions, yeah.
Thank you, sir, for your valuable time and this lovely talk. If any participants have any questions, so you can ask your question in live chat. We will put your questions. And very soon we will also give a feedback form on live chat. On the live chat, we have shared the feedback form. Please fill that feedback form. On the basis of your filling feedback form, we will send you all the certificates. And I think, sir, no one has any doubts. So no one is asking on live chat. So we think we should conclude here. And finally, we also thank you again.
Thank you, Ajay. Thank you.
Yeah, thank you, sir.
Shall I left from the room?
Yes, sir. Yes, sir.